Okay, so well, this is the quantum information and coherence talk. And for those some new faces I do see here, this is supposed to be a tutorial level talk covering various aspects of quantum information, now imaging, coherence, and so on. So today our speaker is Hugo Defienne. Hugo, did I say the name correctly?
Defienne.
Wow, I was just saying it all incorrect all along.
Just simply Defienne.
Defienne. Okay, fine, thank you. All right. So, well, I'll just repeat Hugo so that there is no confusion.
Stay on, Hugo. It's fine.
Right. Okay, so Hugo did his PhD from Castler Brussels lab in France, where he pioneered the use of quantum optical states in scattering and complex media. He then had his postdoc from Princeton University in USA, where he worked on quantum imaging and worked with structured illumination approaches. In 2019, he got the Marie Curie Fellowship and then took a postdoc fellowship at University of Glasgow. And in the same year, he also got the lecturer position at University of Glasgow. In 2021, he got the ERS award for exploring quantum microscopy with entangled photon pairs. And since 2022, he is CNRS researcher in France at the Institute of Nanosciences at Sorbonne University. And today he's talking about quantum imaging meets adaptive optics. So Hugo, over to you.
Thank you very much, Alan. And thank you very much for the invitation. It's a great pleasure to talk to you guys. As Alan was saying, yeah, so I'm a CNRS researcher at Sorbonne University, and we explore a little bit the field of quantum imaging. And so today I'm going to talk about a bit broadly about quantum imaging at the beginning, but then I will really focus on one specific aspect of it, that a work that we have recently done in the team, which is at the crossroad between quantum imaging and adaptive optics. And I know it's 4 p.m. on your side, and you are probably all you have passed the lunch, so you are awake again. But in case you want to just have one message from the talk that is coming, in case, I don't know, you fell asleep during the talk, I don't know. The main message of the presentation today will be the fact that I'm going to show you how we can use entanglement to improve aberrations correction in microscopy. That's my main message. Catch it, and then if someone asks you after what was the talk about, you can just say that, and you're going to be fine. All right, but for those who want to focus and go a bit deeper with me in this work, the presentation will be, as I said, divided in 2 parts. So I will first really give a very broad, brief introduction about quantum imaging, essentially trying to explain you what is quantum imaging and what are the goals of quantum imaging in general. And then I will focus really on one specific work that is inside this quantum imaging field, where we try essentially to combine adaptive optics and quantum imaging. Of course, I'm open to question anytime, so please stop me. And sometimes I also do not see very well when there is a raised hand, so please do not hesitate to just stop anytime, and I can stop and I can explain you a bit more the concept. But I will really try to go like step by step and be very very detailed in all what I want to say, but also not talk too much and focus on one specific topic. So let's first talk a little bit about quantum imaging, and let's start again with the photo that I put on my first slide. So actually this sort of artistic photo is not from me. It's a photo that has been published after a work from a research group in Australia, the group of Warwick Bowen, where they published this paper that is entitled Quantum Enhanced Nonlinear Microscopy. And then after, if you look into the press release and stuff, you can see this nice image of a microscope. Well, it's interesting because here you can see the different elements of what is composing a microscope. So you have obviously an optical source there. You have your sample. And here you have, let's say, an objective, a microscope objective that is part of the design of your microscope. And something that you do not see here is the detector. Okay, so that's essentially all the important ingredients that you have in an imaging system, and in this case, in a microscope, because I take microscopy as an example here. Well, and in the work, let me give you a bit more detail about this quantum imaging work that has been done in the past. In their work, what they have done, they have demonstrated that it's possible using this microscope to do Raman microscopy. So the microscope was a bit more complex than that, but I won't get into the details. So using a Raman microscope, so probing essentially the vibrational structure of samples, they were able to obtain an image of a yeast cell. Here it's just a yeast cell. And what they achieved is that they were able to obtain an image with an enhanced signal-to-noise ratio compared to what you can get classically. So their work, they show that if you use a classical Raman microscope, you get the same image, but with a lower signal-to-noise ratio than what you use it with their quantum version. How they did that? So the main aspect of this work, and generally this is an example of that illustrates many work in quantum imaging, the crucial point is, of course, the source that you use here. To see it very simply, to build a quantum imaging system from a classical one, you just replace the classical source by a non-classical source of light. In their case, they use bright squeeze light. Okay, and they use bright squeeze light, so they replace the source in their Raman microscope, and in the same time, at the output, they perform a very specific type of detection that was shot noise limited. And by doing that, they were able to show that the image that you were getting was really better in terms of signal-to-noise ratio. In fact, the noise was a bit lower in the case of the quantum version. And that provided them an advantage compared to what you can get classically. But also, this case, so here I just come back to the different aspects of the quantum imaging system. So the non-classical source is the important ingredient. Shot noise floor detection was in this case adapted to the bright squeeze light. So non-classical source and adapted detection are essential. For that, you get a specific advantage. But what is important also to keep in mind when you do quantum imaging is that you always have practical constraints. In their case, they only had an advantage if you operate the classical and the quantum system at the same intensity. If you increase the intensity of the classical, then you get better than the quantum. So if you operate at the same intensity, same flux of photons, then it's good. The trick in this paper was the fact that they managed to get a sample, so a yeast cell, that was damaging at around a bit less than a milliwatt. And so they were able to put the quantum and the classical exactly at this limit and show that if you go higher with the classical, you damage the sample. So they were able really to get something better with the quantum in an absolute way, in a certain sense. Again, that was just the start of my presentation, because I thought that this work was really illustrating very well, broadly speaking, what quantum imaging is about. In quantum imaging, you use non-classical source of light, you exploit quantum properties of non-classical source in order to improve the performance of classical imaging, but you always have to remember that there are some constraints where you effectively have an advantage. So bright squeeze light in this case was used, and it's not really what we are doing in our team, but this is one, let's say, type of non-classical source that has been used so far for quantum imaging, but there are some others. For example, maybe you are aware of some work that has been done recently, probably maybe 5 years ago, by the group of Danoron and also other group, where in this case, it was another type of let's say, quantum imaging, another type of non-classical source used that was single photon emitter. So they were marking biological sample with some quantum dots, and these quantum dots were emitting single photon, as actually most of quantum dots you have, but generally you don't care about their single photon property. But in that case, they cared about it, and what they did by measuring not only the intensity, but also the lack of correlation that you have in the single photon Fock state, you can effectively get an improved resolution on your sample. This case, it was a scanning microscope. So that's another example of the source. And the last type of source that has been used also a lot, in particular in the last 5 years for quantum imaging, were the source of entangled photon pairs. So to produce entangled photon pairs, I will come back to that later, but we call them entangled photon pairs, but in most of the case, it's a two-mode squeeze vacuum state that we approximate as entangled photon pairs. And these sources have been used really in many different they are at the origin of many different quantum imaging configuration. And here I just again took an example from the literature, a very recent one, where they manage, it's a group of Liang Wang in Caltech, where they essentially applied some technique that were already demonstrated with photon pairs that improve, let's say, contrast and resolution compared to classical techniques. So here, that's the image of some cell that they observe in a conventional classical illumination intensity. But now, if you are starting to measure not only the intensity, but also the correlation between the pair, you can retrieve an image with a better resolution and better contrast. I won't get into the details of that, but it's essentially illustrating the spirit there. So in our work, in our team, and in the work I'm going to present to you today, it really falls into this subfield of quantum imaging that is doing quantum imaging with entangled photons or photon pairs. And I gave you, for example, this work here where you get a better resolution, better contrast. But again, never forget that in quantum imaging, there is always a price to pay. And the price to pay in this case, the fact that the source of photon pairs are very weak in terms of intensity. So it's only useful you only get effectively an advantage if you have a sample that cannot be illuminated by too much photons. Because otherwise, if you just use classical light and you just turn up the power and you can go like up to the milliwatt, then you get much better resolution, much better contrast than what you can get with the non-classical source, with the photon pairs in this case. So again, there is an advantage, but it's only valid under certain strict conditions. So this is one type of work that you can find in this subfield of quantum imaging with photon pairs. And another work I wanted to mention, it's slightly different in terms of the spirit. It's illustrated here by the setup of ghost imaging. I guess you are all familiar with ghost imaging, okay? So ghost imaging has been developed also first with photon pairs. So you illuminate a nonlinear crystal. In this case, it was with an UV wavelength, and they managed to have like two photons that were kind of degenerated at the output. One photon was illuminating an object, and then you have a bucket detector that detects it. And on the other side, you have a camera. The camera can detect in the visible, and here the single pixel detector can detect in the infrared, which is honestly which is great. And you can retrieve the object by measuring the correlation between the bucket detector and the camera. Ghost imaging has been pioneered with entangled photons, but then can be reproduced also with classical correlation, with basically also a very good performance. But my point here, so the advantage that you get here, as you can see, is slightly different than the work I show you here. In this case, it's more a practical advantage. It's the fact that, okay, when we build this kind of system, we can get an advantage on the fact that we can use a single pixel detector to detect the higher wavelengths, because we don't have very good camera in this. I mean, we do have camera, but they are made of gallium arsenide. It's not a big market yet, so the camera are quite expensive, not that easy to use, sometimes pretty noisy. You need to cool them down, so it's more a practical advantage here. And these two examples I just gave you here, so the one with the microscopy and the one with the ghost imaging, I think they illustrate well the two type of experiment that we find in quantum imaging with photon pairs. Either you have some experiment when you try to improve the performance of already classical imaging modality, bright field microscopy here, so resolution, contrast, or either you are actually trying to develop new type of imaging modality that at first do not really have any classical counterpart, but then inspire more work later, and it typically inspire also classical imaging, as it was done with ghost imaging. And there are many others. So here, just two examples of really a broad field of people actually trying to develop quantum imaging scheme with photon pairs. There have been some realization of quantum illumination. Imaging with the detected photon was a big thing also in the past years. Quantum holography, phase microscopy, hyperspectral imaging, and so on. So really, there are many different works, and that fall into these two subcategories. And the one I'm going to talk to you about today is really falling into this, also falling into this subfield of quantum imaging with photon pairs. So now let's go to what I want to talk to you about today is this work when we try to merge quantum imaging and adaptive optics. But before that, if you have any question about the very broad introduction I made about quantum imaging, please feel free to ask now, and then we can move into deeper into the details.
Okay. Any question? Well, one quick question I have.
Yep.
The one that you showed for the entangled photons,
Mm-hmm.
how do you detect it, right? You have to have either coincidence or two photon absorption. So what was done in that paper?
So the paper on the left there, yeah, this one, yeah. Oh, it was literally it's a bright field imaging configuration. So you just send photon pairs, and they get, they go through the sample, and you detect the pairs at the output, okay? And to build, so if you just do an intensity measurement, you get the image on the left. I mean, it's nothing different than simply a normal bright field microscope with an amplitude object at the end, okay? So that's the one on the left. To get the one on the right, instead of measuring just the intensity, so just measuring photon counts, you measure correlation, and you put yourself in such a configuration that the sample and the camera are in plane where the photons are strongly correlated, so are in plane of in this case, sorry, inverse way. So you are dividing your, the setup was a bit more complicated than that, but at the end of the day, it's the same. You measure correlation between photon pairs and you build the image from the correlation. In their configuration, they had the sample onto one side, so they were in the far field of the crystal. The sample was on one side, and they had a reference arm, and they were measuring correlation between the reference arm and the sample arm in order to build this image here. All right. And again, it's not new in a sense that this is just the typical square root of 2 that you get by measuring correlation between photons on the camera.
So it's a typical ghost imaging kind of setup, right? Two arms
Yeah,
and then you do. Okay.
exactly. Ghost imaging, but with two cameras, if you want. Instead of having a bucket and a camera, you have a camera and a camera, and you correlate all the symmetric pixels with each other.
I see. Okay.
You see, so it's literally exactly as you said. So ghost imaging with two cameras, and since you are in the far field, you have half of the beam. I mean, you can see the ring like that, and you can imagine the ring cut in two. In their case, they tilted slightly the crystal, so they have a disc instead of a ring. That's why you have this sort of a disc shape here. And they had two discs, so they physically separated the disc, but you can also image them onto the same camera and just draw a line virtually in the middle. And you correlate the photon, the symmetric pixel there. And if you measure the correlation instead of just acquiring the intensity there, you get effectively a bit better resolution. That's true again, which is only true if you accept the fact that if your comparison is done with the same photon flux.
Okay. So this camera, I mean, it's a multi-pixel, but it's still a click detector, right? It's not detecting the number of photons. It's just a click detector, right?
So in this case, they did the experiment with an EMCCD camera.
Okay.
Right. So single photon sensitive, and they were able to effectively extract the coincidence from it.
Okay.
Actually, I think I will have the setup of this at the very end of the presentation. So if you want, I can show you the setup they did. But
okay.
But it was
We'll wait for you to come to the slide. But there's one more question. A second. How? So the question is, how long does it take to get the image like that? That one day they have the G2 image.
So the G2 image, yeah. In their case, they had it in I think half an hour.
Half an hour, I see.
Yeah.
Okay.
So they kind of improved a little bit or at least they say that they improve the first. So I think one main thing in this experiment that they did, they were pumping at the deep UV, and so they were getting photon pairs at 532, which is already great because then you have something in the visible, so you're really hitting really the good window of the camera. And then they improved a little bit the algorithm for measuring the coincidence with the MCCD so that they were able to get something in half an hour with let's say a good SNR, as you say there. Okay. But yeah, typically half an hour. So that you don't have more than one photon.
So Hugo, so the next question is, the rate still needs to be at the single photon level, right? You need to be at the level where each pixel is getting one photon or less than one photon per frame, kind of, right?
Alors, the way they did it, yes, but in reality, no, you don't need to do that. So we have shown that actually if you are, so there are different regimes where you do this coincidence counting. So let's say the ideal case in your head, the way you want to be first is just to be, you take a frame and in the frame you either have 0 photon or 2 photons. Okay, that's the ideal situation, because then in each frame you can really tell, okay, that's my pair, that's my pair, that's my pair. So that's the ideal configuration. But if you try to do that, essentially, it takes you ages to get the statistics of the pairs, because the frame rate of the camera is not that good with the MCCD I'm talking here. So the strategy that you can use is you let more pair per frame. So you increase a bit the exposure time, and in each frame, you have multiple pairs. So you don't know which one is which one. So it means that you have many accidental coincidences as well. But you take many, many frames, and then you, in post-processing, you estimate the accidental. I go quickly on that, but what you do, you correlate the photon within each frame, and then you cross-correlate the photon between different frames, and with that you can effectively remove the accidental afterwards. So that's the second regime you can be, and that's the regime they are, and that's most of the regime we use. So we let many pairs per frame, so because at the end it's better like that, it's faster. And then actually you can also go in a situation where you use very long exposure time, and you let even many photons per pixel. And what you correlate effectively at the end is just you do correlation between numbers of photons, and it also works. So there is no really, and you get the same result. So there is no, especially when you use the MCCD there, you want to get the best of it, and they have long exposure time, they have low frame rate. So typically you can end up in a regime like that, but the 3 regime work. I mean, except if you have too many photons, then at some point the camera hit a slightly non-linear detection. So I think beyond 2 photons per pixel per frame, it's starting to be non-linear, and the signal that you get is not proportional to the number of photons anymore. And we see clearly it in the frame when you measure it that you have some distortion that appears. So practically there is a limit, but you can go more than 2 photons per frame, and even more than 1 photon per pixel in average.
Well, I guess the question is, I mean, if I increase this entangled photon pair flux,
Yeah.
can I get the same quality image faster?
Yeah, probably.
Okay.
Yeah. That's that's a funny thing. That the thing, it's not, honestly, it was not trivial at first, but yeah, actually you can do that.
Okay.
In this case, in this experiment, I mean, some experiments you can, because some experiments you really need to measure the pair per pair, but in this one you can.
Okay. All right.
Cool. Okay, so I keep going.
Yes.
Yes. So now let's go to the topic of my discussion today, which is this work where we merge quantum imaging and adaptive optics. So as I'm just going to try to, can I hide this? No. How do I hide that? Okay, cool, great. Sorry. So in the work I'm going to show you, I'm going to present you today. It's really so it's really at the crossroad between, I say, quantum imaging and adaptive optics, and we're going to use source of entangled photons as the non-classical source. And more specifically, the properties we're going to exploit here is the entanglement between the photons. Then we're going to merge that with adaptive optics technique. And the advantage we're going to get from this technique is the ability to do aberration corrections using entanglement between photon pairs. And in terms of the framework of application, so we're going to apply that into an imaging system, more specifically for a very specific imaging modality that is label-free microscopy. So microscopy without any fluorescence, without any markers. So here is the framework of the work I'm gonna explain to you today. And let's first go to the problem. So what problem do we have when we are, for example, doing label-free microscopy? Let's say I'm a biologist and I want to take a very detailed image of a leg of a grasshopper. I don't know, like a biological sample. So, I know that I have some skills in optics, so I'm going to build a microscope. So I just build a microscope, and a very simple one, a bright field transmission microscope. Very simple. You have a sample, just a source of light here, and I put a camera there. Okay, if I do that, and I do it pretty well, what I expect to have is an image like that, with pretty good resolution. I mean, I can do better than that, but that's already not bad, where I see some structure of my sample. And ideally, if I build correctly my system, there is no aberration. Okay, so I see it well, I see the structure, I can tell something about that. That's I'm happy as a biologist there. But then if there's some misalignment in my construction, or if the sample is not well prepared, that is a bit more thick than what I had at first, what I thought to use, then I get some aberration, and at the end of the day, my image is blurred. And this is very annoying because I cannot tell that much from this image. It's very blurred. I don't see the structure. I essentially lose completely the purpose of using a microscope for observing my sample and observing the small structure. So I have a problem. And as a biologist, I look in the literature a little bit and I see that, actually, there are some people doing adaptive optics that can help and remove this aberration. Great. So I look. And I know adaptive optics, I need to essentially put something into my microscope on the imaging path that will correct for the aberrations. It could be a deformable mirror. It could be also just a spatial rate modulator, because that's what we're going to use typically in our case. Sorry, I just lost the window there. Yeah. So spatial rate modulator. And then I keep looking in the literature, and I need to know. I want to learn how to use it. So I know that adaptive optics the origin comes from astronomy. So I look a bit more into astronomy. So how do we do that in astronomy? In astronomy, what you have similar problem, but you look at the stars, look at the sky, and the light that you measure when you put the telescope on Earth is subject to aberrations, because you have fluctuation of the refractive index in the atmosphere. And because of that, you have, sorry, I'm going to just close the door. Sorry, because there are a lot of noise in the corridor. Sorry for this interruption. Oh. And so the way they do that, so they have some aberration, and then you get an aberrated image of the sky. How do they correct that? They use a concept that they call a guide star. A guide star is that you pick up either one of the stars in the sky, or you actually use your own laser and use it really as a guide star. And from this guide star, you know that this is supposed to be a point-like object, okay? And use the guide star as a point-like object, and you measure the wavefront, the aberrated wavefront, directly with a wavefront sensor, and you correct the wavefronts using a wavefront corrector. And when you correct that, you correct the guide star to make it back to a star, to a point-like object. And using that, then you have effectively the whole image corrected. So let's say you are using guide star also in microscopy, which is something that we do. Let's try to find a guide star in this sample here. For example, you can assume that this little structure here, maybe it's a point-like object. So you can maybe take it, extract it, focus on that, and decide, okay, let's try to maybe optimize the intensity, in this case, decrease the intensity in this specific point, so that it will correct this part, and then in the same time correct also the whole image. So that's guide star, let's say guide star based adaptive optics, and it works. It works many times, but when you have a sample that is label free, so there is no fluorescence, it's actually not that easy to find a point-like object, because it's strongly dependent of the type of sample you have, and also the type of imaging modality. Not all the sample will have this guide star in them. So, okay, so if you cannot use a guide star, then you can also continue looking in the literature and find another technique that it's called image-based adaptive optics. In this case, you don't try to find a guide star. You just take the image at the output and look for specific properties of the image. You compute, for example, a value that tells you what is the contrast, what is the sharpness, the frequency content of your image, and you optimize on these properties. Again, you do some loop with the spatial rate modulator until you optimize this value, and you hope that it will converge to a better image and will correct the aberration. But again, this is again a bit annoying, because it's strongly sample dependent and modality dependent. You actually don't know really. You are not supposed to know what the sample looks like. So maybe you will end up into something that is maybe not your sample, but okay, look maybe sharp. So and if you look at the literature, honestly, the choice of the metric when they do adaptive optics in microscopy like that is really not very clear. They choose the one that works because they have a prior information about their object. So as you can see here, guide star based or image based approach in the case of label free imaging are very difficult to implement. And in this presentation, I will show you that we can actually use another approach that is guide star free and also do not use any image metric, that use source of entangled photon pairs. So we're going to replace the source of classical light by a source of entangled photon pairs. And instead of only measuring the intensity at the output, we're also going to measure the correlation between the photon pairs. And from this correlation image that I will explain you how to build that, we will have a direct information about the point-spread function of the system, and therefore direct information about the aberration. And once we have this information, we will be able to implement the adaptive optics, so like the feedback loop onto the spatial rate modulator, in order to bring back the correlation into sharp correlation. And by doing that, we will also in the same time correct the aberrations. Okay, so that's really the technique we're going to use. That's our solution to the problem of adaptive optics. Again, here I want to remind you that microscopy is a very broad field, okay? I'm really talking here about label-free microscopy. So there is no fluorescence in my sample. If you have some fluorescence marker in your sample, it's much more easy to do adaptive optics because you can be guide star guided. In the case of label-free, that's where you really have a lot of problem. And that's really the subfield we are targeting here. And also, I'm not saying that image-based and guide star technique doesn't work. It's just they don't work all the time. Okay, so the solution we brought here is really sort of an add-on that help really doing adaptive optics in label-free microscopy. But it's better if it's combined with the other technique, right? So let me now explain you how we do that in practice. And but what I want you to remember from this very first part of the presentation is that adaptive optics is a technique that has been used in astronomy first, but also used in microscopy to remove aberrations and get back a sharp image of your sample. It's very difficult to apply it in label-free imaging because you don't have this guide star that you can find. And in our case, we're going to use it. We're going to use entangled photons to actually do adaptive optics. So let's go to the general concept. How does it work? How can we use actually entangled photon to sense aberrations? Okay. Oh, yeah.
Hugo,
yes.
One question. What is
Absolutely. It? Go for it.
How do you introduce? Okay, so how do you introduce aberration in the lab setup?
Ah, okay, yeah. So in general, let me go back to the aberration. Good point, very good point, yeah. So I can tell you how we did artificially did the aberration in our case because we wanted to do a demonstration, but more generally, aberrations can come from there are two origins of them in label-free microscopy at least. Either it's because you have aberration due to the optical components of your imaging system. It could be aberration in microscope objective, it could be misalignment, it could be defocus, all of this in a very complex microscopy system. It's difficult to align, so you can have that. Okay, we call that generally design-induced aberration. And you have also specimen-induced aberration, in the fact that sometimes you have some specimens that are thick and you want to image inside, or you have some surrounding layer, you have a support, you put the sample onto I don't know, in immersion, for example, you are inside a liquid and you have some aberration due to the liquid. So all of these, let's say, surrounding tissues and extra structure that you have sometime around the sample that you want to observe, they create aberrations, okay? So that's aberration in real microscopy. Then, answering more precisely your question, aberration in the lab, how do we produce them artificially to study them? We do it in two ways. Either we use actually a spatial rate modulator in the pupil plane to produce artificial aberration, to kind of mimic the aberration, or we also actually literally put some layers of aberration inside the system. Typically, we use PDMS. And it's a polymer that if you put it around the sample, it mimics very well actually the type of aberration you can have in let's say in a structure when you have the sample and a matrix of let's say liquid or aberrated tissue around it. That's the two way we do that.
Okay. Okay.
I will show you some picture if you want of the PDMF and the artificial aberration we did for the study here.
Okay.
Okay. So, okay, but that was really the broad thing. So I haven't told you anything yet. You don't know. I told you what I'm doing, but I haven't told you how we do it. So let's go on the how now. How we do it. Sorry, back there. So how do we actually use entangled photon to correct aberration? And in fact, we do not actually use, we correct the aberration using like adaptive optics, but the purpose of using entangled photons here is to measure the aberration in the system without the need of a guide star, without the need of image-based AO. And before to get a bit more into the details, I think the main concept can be understood very simply with this very simple diagram that I'm showing you now. Let's consider, take a step back, and you assume that you have some light propagating through a system when you have some aberration, okay? So if you, as you know, if you arrive with coherent light that has a flat wavefront, what the aberration does, they essentially perturb the wavefront of the light. So you have, let's say, your collimated laser coming here, and you have the aberrations, and then you have an aberrated wavefront, and then upon propagation, it will interfere and create a complex structure. So instead of having something that will be collimated at the output, you're going to have sort of a speckle at the output or something, scattered around. Right. So that's the vision with coherent light. I think we understand all about that. But now I would like you to take a particle picture of the system. So let's forget about the thing that it's a wave and think about the light as a flux of particles, very simply. So you send a lot of particles through your aberrations, okay? Photons, and what happens when the photons hit the aberration layer? Essentially, they get they get deviated from their initial trajectory, okay? And so you have the photons arrive there, they get deviated like that, and they follow, of course, the statistics of the corresponding wave. But in a certain sense, you can clearly see that if you come with a flux of photons that is completely uncorrelated, like randomly distributed, well, at the end, they're going to be deviated randomly as well, and you're going to also have uncorrelated photons at the output. So nothing's going to change in the correlation. If you have uncorrelated at the beginning, you're going to be uncorrelated at the end after passing this random disorder, okay? And I think the very simple message in what we do is simply that instead of coming with uncorrelated photons, we come with some light that has some correlation, and the photons are correlated. And when they pass through the aberration layer, they essentially lose their correlation. And that's exactly what we measure at the end. What we measure in this whole work, we just actually sense the loss of correlation that we have in our photons in order to infer what are the aberrations. And if we know the aberration, then we can correct them. Very simply. So keep in mind, even if after I will be a bit more technical than that, but keep in mind that the very simple picture is that you send a random flux of photons onto something that essentially scatter them in all the directions. But if you send them correlated, they lose their correlation. And if you measure this correlation, then you can have some information about the aberrations. The very simplified way of thinking about what I'm going to tell you over the next 20 minutes, okay? Let's go now more a bit, into the details, into the concept, how does it work? And let's take a very simple imaging system.
Wait, Hugo, one more question.
Yes, of course.
How to, what is the difference between the aberration and actual image, which will also
So in this cartoon, what is the difference between the actual
image, the sample that's being released and the aberration? If the image causes uncorrelatedness, what will ever capture?
Yeah. So if the image itself is causing aberration or the uncorrelation, how will you get that back?
Yeah. Oh, we will get there.
Mm-hmm.
We'll get there soon.
Okay.
Okay. It's a very again. This is really a cartoon. The physics there is very, very, very vaguely. Now, it's just to tell you, in a sense, that's what taking a big step back. That's what we do. We just throw some particles onto something, and because there are some aberration, they get uncorrelated, and we're going to try to measure the correlation and get back to the aberration. But yeah, let's say more accurate description will come just after. This is just for you to keep an image in your mind.
Okay.
Okay, let's go a bit more specific then. Let's consider a situation, very simple imaging system. Okay, it could be a microscope, but I just simplify it with two lenses. And here you have the sample plane, you put a sample there, and you have the camera plane, okay? You illuminate your system, in this case, with a source of entangled photon pair. So you can see really this as a flux of photons coming onto your sample, but in the sample plane, make it simple, the photons are strongly correlated, okay? So it acts as if in the sample plane, you had actually many sources here, okay, that all emit photon pairs. We can really think of it like that. Again, it's still a thought experiment. I will come back to the experiment later, how we do that in practice, but let's think of it like that, okay? You have a sample plane where each point is essentially emitted photon, but per two per two, okay? And you do that, you run your experiment, of course, you have photons emitting, it's a quite low photon flux, you have photon emitted pair, and so on, and you want to build an image at the output, so you use a long exposure time, typically, okay? Nothing really special there. You accumulate the photon onto the sensor, and at the end, you get an intensity image. Again, this is exactly the same thing you will get classically with a classical source of light, okay? Nothing special. I didn't do anything different. If I replace the source of entangled photon pairs, I get exactly the same intensity image here, okay? But that's a long exposure time, so I essentially accumulate photon onto the sensor to build an image. Great. And in this case, it's the image I had before with no aberration. But now let's do something slightly different. Instead of averaging, accumulating many photons to build the image, now I'm going to try to measure each pair, the signal pair. So I managed to have a very short exposure time, and I get a pair onto the sensor. Okay, so I get 2 clicks. Everything is ideal there. No noise, no loss, perfect. I get a pair. Okay, this pair has been emitted from this, from this point here. And the 2 photons, because and it's an imaging system, so a point is supposed to be a point. In fact, a point is not a point. A point is actually the PSF. It's a diffraction limited spot. So the 2 photons, the probability for the 2 photons to arriving somewhere in the camera plane are within the point spread function of my system. So within the width, the diffraction spot, okay? Normal so far. But in this case, the 2 photons arrive in the diffraction spot, okay? But they have a little bit of, let's say, flexibility because the diffraction spot is not infinitely thin. So the 2 photons can arrive with a certain distance between them into this diffraction spot, which is the what I call sigma here. And let's say that for each pair we detect on the camera, now we measure the distance between the photon, okay? So we do not only count them, but we measure actually the distance between them. So this delta R that I wrote there, and I draw a new image, okay, where every time I have a pair detected on my sensor, I just put a point for the distance between them. So in this case, the distance is pretty short, so that's the 0 in the middle. So if the pairs are very short, delta R is almost 0, then you are close to the center here, okay? Well, let's do that. So I do it for 1 pair, but then I manage to have my system so that I measure pair. And I keep getting the click there. Okay, so for each pair I get on the sensor, I look at the distance between them. Okay, tack. So I accumulate, and then I get at the end, if I do that experimentally, I get something like that with a sharp peak in the middle. Why there is a sharp peak in the middle? Because as we said before, the 2 photons, they arrive anywhere onto the image plane, but they always arrive within the PSF. So they always arrive together within the sigma that is effectively the diffraction spot. So at the end of the day, the image that you build when you measure the photon pair, and you look at their correlation, so the distance between them, it has a width that is effectively the width of the point spread function. In fact, it's not exactly the point spread function. If you go through the math, it's the autocorrelation of the point spread function, but never mind. It's more or less that. So the width that you have here is the point spread function. Of course, here I just show you a case where there is no aberration, okay? Because the photons always arrive within the PSF. But then you see me coming. If you had some aberration in your system there, what's going to happen? The PSF is gonna broaden a little bit, gonna get broader, and instead of having a sharp peak here on the correlation image, then you're gonna start having. So not only you're gonna start having the intensity image gonna be a bit blurred as we saw before, but not only that, you will also start seeing some spread of the correlation image, because the correlation image is a signature of the point spread function, and the point spread function is directly sensitive to the aberration of your microscope. If your microscope is diffraction limited, you expect to have a sharp peak in the correlation image. If it's not diffraction limited anymore, because it's subject to aberration, then you have a distortion of the correlation image. Okay, and here, this distortion of the correlation here is a direct signature of the aberrations that you have in your system. And this is exactly what we're going to use to implement the adaptive optics system. Okay? Before I move on, so that's an important point. I will go into the technical detail after, but if you have a question on that, you can ask it now.
Yeah, there is one more.
So,
Yep.
this will work only if you have static aberration. If you have dynamic aberration, it won't work with that.
Static. Yeah, so far I'm only talking about static aberration, okay? Because, or it has to be dynamic, but within a typical time that is longer than the time it takes for me to accumulate enough pair to get the correlation image. If it moves during that, I mean, if it moves during that, it's fine in the sense I will still get something aberrated at the output, but the problem will be actually to compensate it. And that I will come to that later. The correction part need to be faster than the time the medium decorrelate, okay? But if it moves during the time, you're gonna still get the correlation image that's gonna be blurred. But in this case, I'm considering only static aberration for simplicity.
The assumption here is that the sample is thin enough that the entangled pair actually leave the sample together.
Yes.
Because the entanglement is behind. I mean, the pair came from behind. It's a transmission problem.
Yeah.
Okay.
Very good.
Assume? And is that
Very good question. Yeah. So I will come back to that later. Effectively, so in the system we do, we effectively to make them, you have effectively the best configuration you want to use is a situation where your sample, or at least the plane of interest, is imaged with photons that are as strongly correlated as possible. Okay, the way we do that experimentally is that we effectively image a specific plane of the crystal onto the sample plane, and we want to start from correlation that are as sharp as possible in the sample plane. It's a good point. But even if they are not that sharp anyway, as you will see, the correction will still work. It's not a big deal if they are, if they are really limited by point, because it's not true. They are not limited by point object in the sample side. They are already a bit broad, but it's fine. The next problem, it's fine if it's a bit broad. The only problem you may have is if you have too much aberration also on the illumination side. But I can come back to that later, because so far I'm telling you about aberration mostly on the imaging side, which is from the sample to the camera. If you also have onto the illumination side, then it's a bit more complicated, but it still works. Okay, all right, we keep going then. So a little technical detail here. I've told you the story as we just discussed, the fact that in the explanation and in the result I'm showing you there, the photons were effectively strongly correlated on the sample plane. Okay, so in the plane where I put this grasshopper leg, I built my system so that they were really correlated there. In a sense, I was imaging the surface of my thin crystal onto the sample. Okay, but in fact, in most of the experiments we've done so far, we use a slightly different configuration where the photons were not actually strongly correlated, but actually strongly anti-correlated. And for that, we were effectively imaging the far field of the crystal onto the sample. And the reason for that is purely technical. It's purely due to the fact that it gets a bit better signal on the correlation image if you are in the anti-correlation configuration rather than the correlation configuration. And at the end of the day, it doesn't change anything. So you start with a sample that emits photons that are strongly anti-correlated. So when one is emitted here, its twin is emitted exactly at the symmetric. And instead of looking at the distance between the photon, what you look at is the barycenter of the photon. Because if there is no aberration, the photons are strongly anti-correlated, so they always start at symmetric pixel and they arrive also at symmetric pixel, perfectly symmetric. So the barycenter is at the 0, always center. It doesn't matter which pair, they're always anti-symmetric. As soon as you have some aberration, then they get a bit scattered around each of them, and then the barycenter of the photon gets a bit broader, and that's also the way we probe the aberration. So I mean, just to show you that, because most of the experiments I'm going to show you later have been done with this anti-correlated configuration. That's an example. You had, again, the same intensity image that were blurred. And instead of measuring the distance, what I call delta x, delta y. In this case, it's delta x plus, delta y plus, which correspond to the barycenter of the photon there. And again, as you can see, you have a broad peak because in the presence of aberration, these get broadened. That's it. But again, conceptually, it's the same. We're looking for a change in the correlation structure to probe the aberrations, just slightly different configuration. And to be a bit more specific about that, so again, the equation slightly change again, correlation become convolution, but overall the information is there and we use it the same way as if we were using correlated photon pair in the sample plane. We did some experiment with correlated photon, but it's just practically a bit easier to do it with anti-correlated photons. So that was really a technical point. And now let's get a bit more technical and get really into more into the experimental details of how do we actually produce this source of entangled photon pairs. How do we produce source of photon pairs that are anti-correlated? And to do that, I'm assuming maybe most of you know that, but I'm going to go through it. To produce photon pairs in our case, we use a nonlinear crystal, and it's simply a beta barium borate crystal. So a thin crystal, typically half of a millimeter thickness, then 1 millimeter by 1 millimeter. And we just illuminate it with a collimated blue laser. So CW laser, collimated, 1 millimeter diameter, for example. And the crystal has a non-zero chi2, which enables the production of photon pairs through spontaneous parametric down conversion. Okay, it means that from time to time, you have one blue photon that becomes two red photons. Okay. And so by SPDC, you can produce this pair. As I said at the beginning, in fact, you are actually producing a two-mode squeeze vacuum state. But here we are in the low gain regime. So the pump is typically between 10 and 100 milliwatts, 1 millimeter diameter. So we can effectively neglect all the stimulated emission that produce more than two photons and only keep in our mind that we produce only pairs of photons at the output. And if we go in a far field configuration, as I said, that's the one we use. So we go, let's say, far from the crystal, or we can use a lens, to image the Fourier image of the crystal. If you go far from the crystal, what you see from this pair is that they are always strongly anti-correlated. When one photon is emitted in one direction, its twin is always emitted in the symmetric direction. Okay, that's due to momentum conservation. And the fact that you have strong anti-correlation in the momentum and in the same time strong correlation in the position, because if you look at the surface of the crystal, the pairs are strongly correlated. These two things are a signature of spatial entanglement in your source of photon pairs. As I said, we use, in our case, we're going to put ourselves in, essentially focus on the anti-correlation. So let's put a camera in the far field of the crystal, so far from the crystal or after a lens that does a Fourier transform. And in our case, we use single photon sensitive camera such as the MCCD. They are not the best. I mean, we did the work with that because that's what we had at the time and we kept doing that, but actually we have better camera and you guys also have it actually. We'll talk about that a bit later, but let's do it with an EMCCD camera. And again, let's start with an ideal configuration. The way we want to do it is that we have some pairs arriving on the sensor and we want to be in an ideal configuration where we get one pair per frame. And of course, you get many pairs. If you sum all of them, you just get an intensity image. So in this case, there is no sample, just a broad intensity. It's not a ring because we slightly tilted the crystal so that it becomes a bit of a disk because it makes it a bit more homogeneous. It's better for imaging. But then, as I explained before, instead of doing just the sum of the photons, you can also measure the barycenter in each of the frame. And if you measure the barycenter in each of them, then you can compute, as I've shown you before, this correlation image that show a sharp peak at the center when there is no aberration of the system because the photons are strongly anti-correlated, okay? This was an ideal situation. One pair per frame never happen when you do imaging with an EMCCD camera. And I was saying before, in fact, with an EMCCD, you get into a regime where you typically use, let's say, tens of a millisecond of exposure time, full gain. And what you collect on the camera is not only you have multiple pairs that have hit the camera during the exposure time, you also have some noise. You also have some single photon that come from the ambient light and also come from the fact that sometimes you have losses that kill one photon of the pair. So you have many other things than just the pair. And the way we do that, we measure many images like that. And then we process this set of images so that we get only at the end the correlation between the pairs. It's not explained there, but I can come back into details of how we do this processing. It's essentially subtracting accidentals, a bit the same way as we do it when you do subtraction of accidental with single pixel detector, but here at the level of the frame. But keep in mind that this regime there is what happens when you use the MCCD camera. You have many pair per frame. But again, EMCCD camera is probably not the best choice today for this kind of thing. And we have been using another camera recently that is it's an event-based camera called the TimePix camera. It's composed of an intensifier and an event-based device, a complex camera that essentially can give you a like nanosecond temporal resolution and with a lot of pixels. And the way it works, it's actually interesting. You do not actually measure some images, you just measure a list of events. So you run the camera for 10 seconds, and then you will get a list of events with X, Y, and T. Okay, so X, Y being the position, spatial position of the event, and T it's time during the acquisition. And if you take this string of data and then you process them so that you keep only the photon that arrive within a certain exposure time, certain window, which is 6 nanoseconds here, then you filter out only the pairs. And if you replay again this acquisition, you can see here on the camera, that's really a replay of the acquisition where you see all the pairs coming onto your sensor. And you can see that every time there is a click somewhere, so in blue, for example, there is always a symmetric in red. So the photons really arrive pair in an anti-correlated way onto the sensor. So it's true, like you can also now do some pair correlation measurement. There are some cameras that allow you to do that, okay? And EMCCD is not the only choice when you want to do these kind of things. Just wanted to mention that. If you want, I can go back on the EMCCD processing later, but it's a bit technical. All right, so that's how we detect the correlations with camera, and we produce the photon pairs using this thin nonlinear crystal. What I would like you to remember from this second part of the presentation, so as I said, the spatial correlation will provide between the photon will provide some information about the point spread function and indirectly about the aberration. For that, you need to count the pair in coincidence at the output, or at least to be able to measure their spatial correlation, because that's the information you need to get. And you can do that using a single photon sensitive camera. Okay. EMCCD work, this TimePix camera work, and we also use SPATS cameras, so single photon avalanche diode arrays, that also do the job very well. All slightly different way of processing the coincidence, but at the end of the day, you get the same information, spatial correlation between the photon pairs that you detect on the camera. All right, so let's go now to the experimental result and how do we actually implement the aberration correction in the system. Let's take a very simple bright field imaging microscope. So we have the sample here, sample plane is there. We have, so one lenses, two lenses that image the sample onto the camera. So normal microscope. And in the middle of, inside this microscope, what we do, we induce some aberration, okay? As I say, we can induce it by using a second SLM, or induce it by then putting a random pattern on the SLM, or inducing by putting some PDMS. In this case, it's induced by putting a random pattern onto the spatial light modulator that we position somewhere in the setup. Okay. And to correct the aberration, we use an SLM, another SLM that is in the pulpit plane of the imaging system, so in the Fourier plane of the sample, that will be used to correct the aberration. And on the illumination side, what is important is the fact that we illuminate the sample by Fourier imaging the crystal onto the sample. So on the sample, the photons are strongly anti-correlated. Okay. So I do the experiment. I implemented some random aberration onto my artificially my second SLM that artificially creates some aberrations, and that's the image I get, completely blurred. And now I measure the correlation. So this image typically takes a minute to measure, and I see that my correlation is a broad spot. Okay, as I expect, as I showed you just before. To correct for them, I just select the central point of this correlation, so the middle of this broad peak, and I start optimizing the spatial light modulator onto this value. And to do the optimization, I choose a specific approach that is used also in classical adaptive optics microscopy, that is essentially to correct the aberration by successively programming some Zernike polynomial pattern onto the spatial rate modulator. For example, here what I'm showing is the pattern that corresponds to the defocus. So I scan the defocus, and for each position of the defocus, I measure a point that you can see on this blue curve here. So I measure this point for a defocus of -2, this point for a defocus here, and many points. So I measure 10 points. This takes 10 minutes. Then I have a curve where there is a maximum. Then I choose this maximum by fitting the curve, and I program, okay, that's the defocus with this coefficient. Then I move to the next Zernike polynomial, and I program it the same way. So I keep the first one, and on top of it, I program the second one. That could be the astigmatism, for example. And then I measure the same curve. There is an optimal there. I choose the optimal of the curve, and I program it. And then I keep superimposing like that all the modes on my spatial rate modulator until I actually optimize the correlation and get a sharp peak on my correlation image. And once I got the sharp peak on my correlation image, then I can go back to my normal microscope and just take a normal measurement of the intensity, and I observe that the image is sharp. Because I did the correction by measuring the correlation image at the output, but when I want to use my microscope, I just measure it with conventional intensity image. All right, so this takes, a fraction of a second to be measured, and each image is a minute, 10 points. Let's say you can go down to maybe 5 points per mask of optimization. So essentially, it's an hour to implement the optimization, and this is just almost real-time image that you can get because it's literally direct intensity. Just as a comparison, if you compare to what you had with the aberration and without the aberration, you can see that we really get close to a very good image. That very close to the ground truth that we had by optimizing this aberration. And this pattern here is the pattern, the aberration correction pattern that we have on the spatial rate modulator at the end. You see this very weird structure that is composed of essentially mostly low-order Zernike polynomial modes. Again, in this experiment here, we only consider a case of low-order aberrations. The aberrations were pretty smooth. I can go back later of what happened when we have stronger aberration and close to scattering, which is much more difficult than that. In that case, the aberrations were induced in such a way that it's very smooth. And as I said, we can induce aberration by using a second SLM, and we can also induce aberration by just like putting some aberration layer inside the system. In that case, we sandwich the sample with PDMS that blur a bit the propagation of the photon and create some low order aberrations. That's typically what you can have when you have a sample that is essentially in an immersion liquid, for example, that can really create some aberrations. So that's much more realistic, and you get aberration like that. You see how the correlation is aberrated. We do the optimization, get back to a sharp peak, and we have here the aberration, and that's the ground truth to show you that we get to something pretty close to the best image that you can get when you literally remove the PDMS from your system. And so it works pretty well. A thing that I wanted to mention also, we did a short comparison between what are the advantages of using that compared to classical AO technique. I mean, this takes a bit of a long time because an hour to get the aberration, as you said at the beginning, cannot work with dynamic aberrations. It has to be static at least at this stage of the experiment. We can probably go faster, but we haven't done it. And so it's static aberration. But let's compare a little bit of what you can do classically. And one of the techniques that is mostly used when you do label-free imaging is image-based AO. So you choose a metric and you optimize on the metric. And here are just different results that we have obtained. This one is, so this is the ground truth, and the object that we wanted to image was a bit more complicated than just a 2D sample. It was a 3D sample with 3 wires in 3 different planes, okay? And you can see in the ground truth here, so there is no aberration there, that you had essentially one wire that was kind of in plane, and then this one was really off plane, and this one is in between. So the 3D structure is there. It's a bit more complex. That's the image that you get as the ground truth. And as expected, when you measure the correlation in that case, you have a sharp peak in the correlation, okay? And what we did first an optimization on the contrast of the image. So we asked the system, forget about the correlation, just take the intensity image and optimize on the contrast. Try to get back to the best contrast you can have at the output. The system does that, but converge to something that is a bit weird. Because I mean, the contrast it's dependent of the object you are looking at. And in that case, it converges to something like that that is completely off plane. So it didn't correct at all the aberration that we introduced in the system. And as you can see, when then we measure the correlation, we can see that there is no peak there. And actually, I forget. So that's the image with the aberration that we got. But if we do the quantum correction, we get back to the correct image, exactly the same as the ground truth. So we do not get tracked to some wrong solution when we do the aberration with the correlation, because we have a direct access to the PSF. So we directly correct the PSF without any assumption of the object. And that's just some curve that shows, where the aberration is. So the quantum gives you exactly the right solution that is there. And as you can see, if you use some other metric, contrast, low frequency, or power in bucket, that are other metrics that I use in adaptive optics, you always get to the wrong solution with this kind of very complex 3D sample. With 2D samples that are very sharp and very simple, image-based work pretty well. As soon as you get something that is too complex, it's very difficult to know if you actually converge to the right solution and if what you are looking at is actually what you want to look at, in a sense. So quantum, let's say in that case, the correlation technique works pretty well because it always converges to the right solution. And just to end this presentation, so far I've shown you that we essentially use the quantumness of our source, so the fact that we have correlation between the photons, only to implement the optimization. So the image is taken, the intensity image is taken classically, then we go measure the correlation, do the optimization loop on the correlation, and then go back and take a classical image. But we can also implement that in a fully quantum enhanced microscope. And in this case, that's the microscope from the image I showed you at the beginning. I told you I was going to show you again. So that's the experiment that they built in their case. They had a source of photon pairs here. They separated the two photons and they imaged. So they had a reference plane with nothing there, and they have an object plane here. And then they just program, they just image the two sides of the thing onto the camera and measure the correlation to get the image I show you earlier. So we did exactly the same. We kind of rebuild the same system as they have, but we introduced some aberration in it. So we put some PDMS somewhere in the system to induce some aberration. And we did the measurement. So in their case, if you want to get the advantage of the better spatial resolution they had, you need to perform to retrieve the image through a correlation measurement. So you need to measure correlation to retrieve the image. It takes much long time, but that's what we get when we have some aberration. As you can see, it's pretty bad. You expect to see something that looks like a biological sample here, but instead of that, you have something blurred, not only blurred, with a very low SNR. So it's pretty bad. And this was a long acquisition. This was probably 10 hours acquisition to get something like that. So pretty long. When we use our technique of aberration correction, then we get not only a sharper image of this, I think that's the leg of something. I don't remember what it was, maybe the leg of an insect. After correction, we get something not only sharper, but also with a better SNR. Because when you do quantum imaging and you measure the image via the correlation, the SNR is also strongly dependent of the aberration that you have in your system, which is not the case in intensity. And in this case, it's really a big problem. So you get a much better SNR. If we compare to the ground truth, it's actually pretty good. We have a SNR that is really nice. And in the same time, we don't have actually the best quality in terms of sharpness of the image, but we get to something much better than with the aberration. So here, the highlight was on the fact that, yeah, it can also work in a system where it's actually a quantum enhanced microscope that also uses the correlation between the pair to build an image. And it's useful not only because you deblur the image, but also because you get a much better SNR, which at the end strongly shorten the exposure, the time of acquisition that you need at the end to perform the experiment. So we believe it's also useful, like genuinely in quantum enhanced imaging system that already use photon pairs for improving the performance of the system. So I'm reaching slowly the conclusion of my presentation. I wanted to talk a little bit more about, I've shown you all these things that work. I wanted to talk a bit about the constraints and the perspective of this work. And one thing that has been mentioned before is the fact that so far we have only used the system in a transmission configuration. And we believe that something very interesting could be also to be working in a reflection configuration, in particular combined with OCT, optical coherent tomography. Because if we can do that, we can use OCT plus aberration correction. That will really help because it's not that easy in OCT to implement adaptive optics. The problem with reflection configuration is the fact that you experience the aberration twice, once on the illumination side and once on the reflection side. And actually, we thought at the beginning that would be a problem, but it could work. It could work pretty well. And we did some simulation that actually showed that the aberration correction effectively, because we measure the correlation, pick up really only the aberration, mostly the aberration onto the imaging side. And we can effectively retrieve in this case, it was just a grating as an image, but an image after correction compared to before correction. That's an ongoing work. We are currently working on it. Another limitation of our demonstration so far is the aberration. We only did it with very weak aberration. Okay, PDMS, some surrounding tissue around the sample, typically some transparent tissue. If you take the brain, it's kind of having cell, and the cells are surrounded by a sort of matrix of a liquid that creates some aberration. That could be it, creating only very weak aberration surrounding the sample or very weak aberration inside the microscope. But you have some strong aberration like thick tissue. Typically, the problem becomes much harder. So we did some experiment with a paraffin layer. I mean, it's not thick tissue, but it's more complex than weak aberrations. And we managed actually to measure and to retrieve a peak in the aberration at the output. So we were able to optimize using actually not only MCCD camera, but with a SPAT camera, because it was difficult to start from a very noisy image. That was the difficulty, was to start the optimization. Once you got it, then it converges. But on the same time, you also have some other problem in the fact that you only correct a part of the field of view and not the whole field of view. So anyway, just saying that we are aware of this problem and we are working into getting the optimization a bit better in order to also tackle these cases with more aberrations. Again, the deal really in terms of technical point is going faster. So EMCC camera is really not the best choice here. We're moving slowly to SPAD and Timepics camera to get the optimization just faster. So that we can, it just works better, and it's really a limiting point so far. Before to go to my final slide, when I say thank you to everyone, I just added a bonus slide because there is a question that's probably going to come. Is entanglement necessary in that case to actually do that? Because so far I've only talked about the correlation between the photons. I haven't talked about entanglement that much. I mean, the correlation originates in this case from a source of entangled photon pairs, but I effectively only measure correlations. So the answer to this question is that no, it's not strictly speaking necessary here, but it still gives a different result. If you look a bit through the math, if you consider the case of entanglement, the correlation image that you have at the output is the convolution of the PSF, the coherent PSF with itself. Okay. If you replace the source of photon pairs by source of purely classically anti-correlated photons like that you will generate with two pistols, you just produce photons like that, ideal hypothetical case, but only correlated, then the convolution is between the incoherent PSF. So it's slightly different than when you get, and this small difference gives you a better sensitivity to the aberration, which is easy to understand because in the coherent PSF, you also have the phase information. So if you have some aberration on the phase, they will be probed with the coherent PSF and not the incoherent PSF. So here you have the curve of you create some aberration and you increase the aberration into your microscope, so artificially, and you look at the peak value where you're going to start the optimization. And you can see that when you have entangled photon, it drops faster than when you have correlated photons, and drop faster, of course, than the average intensity of the PSF as well, which is the classical case of a guide star. So entangled photons bring you more sensitivity there than when you had purely classically correlated photons. And on top of that, so it's more sensitive. It's also interesting for doing phase imaging. When you do phase imaging, you want to correct the PSF, but not only the incoherent PSF, actually the full coherent PSF. So that's more likely to happen with entangled photons there. Of course, when you already use entangled photons, like in quantum imaging, it's good to have them and to use them. And it's also actually more simple in practice. I mean, generating this kind of very strongly anti-correlated photons, it's not that easy. It requires a bit of engineering on the source. In that case, for free, you have like a source of perfectly anti-correlated photon by just putting a lens and a thin crystal. So it's compact, it's simple to use, and it's easy to use in microscopy. Of course, the main drawback is the intensity. In that case, you are working the nanowatt regime, which means that as long as you have some losses and some scattering, too much losses, too much scattering in your system, it becomes really difficult to collect the photon at the output, and the experiment become really time consuming and almost unfeasible in a practical way. That's the only drawback we have here. But it's also an advantage if you don't want to illuminate your sample with too many photons. Again, photosensitive samples are very well adapted to this kind of very, very low flux illuminations. So that leads me to my the last point I wanted you to remember from the presentation. So we do adaptive optics using entangled photons. We think that, let's say, it's a new tool in AO, but not like something that's going to revolutionize anything. It's something that's going to maybe be an add-on to all the already existing adaptive optics tools that exist, and specifically targeting label-free microscopy in that case. And yeah, we are working on the fact that we would like to use it more for more practical use in microscopy, in particular in reflection configuration where it could be really useful. So with that, I would like to thank you, all of you, for your attention. Of course, this paper is really a teamwork, and the main actor of this teamwork is Patrick, who is the PhD student who was leading this work. Patrick is here, but the work of all the team was really necessary to build this nice story. Remind you the main thing: we use entangled photon entanglement to improve aberration correction in microscopy, yeah, I would like to, of course, to thank you, all of you, for your attention and for the invitation today.
All right, excellent. Let's Hugo, fantastic work. Any questions? Yes.
So I have a question. So how many Zernikeys you use to correct the example you showed earlier?
Can you repeat? I didn't catch it entirely.
So how many Zernikeys you used?
Zernike, okay. We go up to, we did up to 10, but I think in the result I show you, we went up to maybe 5 or 6, the n number, okay? So it's, you have n equals 0, then n equals 1, then you have a different L, and so on. So in total, the number of modes, yeah, around 10, not more.
Okay, so I have a comment on that. So like in low Zernikeys, like in astronomy, we use in and out of focus PSFs to build the, to find out the aberration. So maybe like, have you tried that?
No, we repeat we haven't tried that, but repeat the wording.
So if you take in focus and out of focus, so phase is just like when you take a derivative, so you take 2 measurements, right? That's
okay,
what
okay. Okay, one
can,
in focus and one out focus. Okay.
Yeah, 10 to 20 Zernikeys up to that, you may be able to, possibly able to recover that.
Okay. Yeah. No, we haven't tried that. That's an interesting point. Yeah. I was not aware of that, to be honest. So let's say the correction part, the adaptive optics part, we didn't work on that at all, in a sense that we literally borrowed that from microscopy. We look at the website of Professor Martin Booth, who has a website of adaptive optics, where you have all the different algorithm that you can use for correcting, and we literally store it there and use it simply. So the same algorithm I use in classical AO. So the improvement is really not on the algorithm itself. There are many improvements that can be done here, I'm sure. We just literally the way we probe the aberration in the system, that's the difference, and that's through the correlations.
Okay, so Hugo, all the images you showed, the ground truth definitely looks better than everything else. So how was that ground truth image obtained? So
ground truth was obtained by literally removing the aberration from the system. So with nothing, like doing the experiment as good as possible. So essentially, if I go back to the image there, the ground truth here was taken, with I was imaging. We built the microscope the best way we could, okay, and took the image. That's how we did it. The sample was quite thin there, and then to create the aberration, we literally introduced some aberration in the system. So we put a PDMS layer, actually 2 PDMS layers around the sample, so that it creates some artificial aberration. That's the second image we took, and then we implemented the correction with the PDMS in it to get the best result we can. It's just to mimic that. If I was using, if in reality, you will never have the ground truth, in a sense. You will only be stuck with the aberrated and the after correction image.
So the ground truth image is also with the entangled photons, right?
Yeah, absolutely. Yeah, exactly. It's also with
Okay.
entangled photon. Yeah, not classical. Yeah, it's the same experiment done, but just removing the aberration in the system.
Yes, Suman.
So the imaging thing is like, I mean, you were doing checking that two photon correlation. I mean, can I consider it's like conditional measurement you are doing? Like you're finding out that where it's conditional is pretty tight, and then you are doing the imaging.
I'm not hearing very well. Maybe get closer to the computer. Because yeah.
So the optimization you are doing, so is it like conditional image? I mean, conditional thing you are finding, and how tight you can find it means two photon correlation. That's what you are looking. And after that, when you are doing the imaging, is it that imaging with just with the down converted photons, or that image reconstruction is happening on the basis of that conditional image?
Okay, I think I'm not sure. I got only. I didn't understand very well your question. So, can you repeat?
So that delta X prime and delta Y prime in
Yeah,
that
yeah.
graph, see that? So
Okay, so
that,
you mean this kind of image here, right?
yes. So this
Okay.
is this is something like how correlated the photon pair is, like that. Right?
Exactly. Yes, exactly.
So after, when you find out that they are pretty much correlated, and then you are doing the imaging thing with the down converted light. Is it the thing, or from here you are reconstructing the image? That's what I'm asking.
No,
Like,
so we do everything. So it's there is always the source of photon pairs in the system. Okay.
yes.
If that, so you put the source of photon pairs in your microscope. You put you arrange the microscope so that it's, with when there is nothing in your microscope, you Fourier image the plane onto the sample plane, and then you image properly. You align things, and then you put your sample in it. Okay, and it turns out that maybe your sample has some aberrations around it. Okay, so you do that, you get your blurred image. Okay, so you are there. The source is always in. Okay, so you start, the first thing you do, you take a normal image with the SPDC light, but a normal image, like an intensity image. You just set up a 1 second exposure time, and you take the image, and that's what give me this image there. Okay, then on top of that, I'm still in the same configuration. Okay, and I'm just, okay, now I'm going to, instead of measuring just the intensity, I'm just starting to measure the correlation. So I use this trick where I measure many frames, and I build the correlation on it, and then I get this image to start with. So when I start the thing, I have two information. I have this one, but they were taken exactly as with the same experiment. Nothing special. This one is the sum of all the frames, if you want, and this one is just the correlation between them. And then once I'm there, still not moving anything, then I start doing the optimization. I continuously measure some correlation image, and I do the feedback on the spatial light modulator. Then until I get there, okay. And then once I'm there, I know I am in the right, probably I'm in a good spot. So then I start looking again at the intensity. Again, I'm not changing anything. I'm just keeping the SLM with the best pattern I have. And I look at the intensity again, and I see my image is better. So the correlation and the intensity image are kind of always taken together. We just use them differently at different moments. Is that answering your question?
Yeah, thanks. Just one follow-up question. So when you are doing the correction for that correlation, what is the correlation you are getting that you are considering as that parameter which you are trying to optimize?
Yep.
So in that time that that sample is present, or sample you take it out and
No, the sample is always present.
Sample is present. Okay.
Yeah. So it's always with the sample. So that's the thing. It's really like a problem that, you are a biologist, you come, you have your microscope, you put your sample, it's aberrated, and then deal with it. It's if you remove the sample, there is no more aberration, but that's not the problem. The problem you might encounter is the fact that you put the sample, and sometimes it creates some aberration on top of the, so, and then try to just like deal with it. And so that's what we do. We deal with it like that. So no, we do not remove the sample.
Another just follow-up question I have is
Yes.
smaller blob gives you the better image kind of thing. So looks like ground truth image, ground truth correlation is little bit slight larger blob than the
Yeah.
upper
You mean-
prediction.
You mean on this one?
Yes.
Yeah,
Even
it's
in
a
the first image also.
Yeah, it's a
on
good point.
what-
Yeah.
Yeah,
It's
on
a good
what
point.
basis?
Well, it's so in this case, it's a bit strange. Like, so it's to answer this question, we thought at first, yeah, it's probably because, even if when we do the system as well as we can, I mean, I'm not a microscopist, so when I line things, it gets misaligned. So even, when I do no correction and with no aberration induced, there is still some misalignment that creates some small aberration. So it's not perfectly diffraction limited. So, and we thought that, by doing the adaptive optics, we not only compensate for the induced aberration, but also compensate by our lack of ability to make a system perfect. So we're actually getting better at the end. But so the peak gets better, but actually the image itself does not get better. By eye, we can see here, it's pretty clear, So here, it could be that it's also, it could be the fact that you can see here it's, in this case, it's a bit technical because when you build the image from the correlation, so it's obvious there. When you make the image from the correlation, in fact, you indirectly post-select onto a specific part of the PSF. So the way we pull out this image, we are probably, let's say, projecting onto the less aberrated part of the PSF we could have at the time, and that's why it's much better here and here. While actually, when we sum over the whole image to get that, it has this little tail here that appears to be less good. I don't know if I was clear here, but and if you go back there, here the same, it looks, and here actually, so here it's sharper here than here. And I think if you look at the image, it is sharper here than here. If you look at this, the contrast is less good, but the sharpness, you see that this thing here, this structure are actually much better than this one. So in that case, in the classical case, we probably optimize also for the correction, for the small misalignment I had when I did the ground truth experiment. So this gets the image a bit better than this. In the quantum case, it's a bit more subtle because you measure a correlation image, so it's slightly different than the intensity image that you have here.
Even the next image, right? Or
even the next one is
no. Maybe one back.
One back, yeah. Which one?
One more back. No, in one of the images. No.
Yeah.
So go forward. Then I think this is probably.
Yeah. This one is the other one. This one is
one more.
They're kind of the same. But this one, yeah, one more.
Yeah, this one. Yeah. No. Go back.
Yeah, sorry.
Yeah, this one. Yeah. So the one with the aberration looks much sharper, right? One
yeah,
with
it's true.
aberration.
Yeah. I mean, but if you look at the image, it looks better actually than the ground truth. So yeah. So it just it's a blind stuff. You just run the algorithm, so it corrects for everything. It corrects for the aberration you have induced and the aberration you have made because you are not an ideal experimentalist and you do not align perfectly a microscopy system. So that's why it gets a bit better, yeah. But it corrects for your mistakes.
Excellent.
Thank you.
So maybe just one last question. Well, so classically you can also beat aberration with adaptive optics, but you require a guide star or some such reference.
Yep.
And now with entangled source, you're showing that you can do it without the guide star. Now, if I compare the two situations, is there any comparison as to which one is better? I mean, suppose if I bring in guide star, the correction that is possible because I have more light there can be more than what we can do here. Is there any comparison like that?
Yeah, I think it's going to be a case by case situation, but it really depends. So for the guide star part, it really depends. So first, the quality of your guide star. Are you sure that what you have is it a bright guide star? Do you see it very well? Are you sure that's a point-like structure? It's not something else, because if you start optimizing of something that is not a point-like structure at the beginning, well, then you will end up to something wrong for sure. So, but let's assume you know your sample is made of point-like stuff, so you're going to find one. Then you do the intensity, the aberration on that. The advantage of doing it classically is the fact that you can go much faster, okay? Because it's an intensity image to take, and the optimization on intensity is going to go much faster than measuring correlation. So that's one advantage classically. One disadvantage you can have is the fact that sometimes, correcting aberration in a region, so you have the guide star in a region of your sample. If you correct the aberration at this point, it will mostly correct the aberration on the surrounding region. So not in the whole field of view, but on a small region surrounding it that is called the isoplanetic patch. And the presence of isoplanetic patch are inherent to the aberration. When you have aberration that are weak but still a bit complex, then you can only correct within a small region around the guide star. The cool thing that with our technique here, we don't have any guide star, and we look really at the problem the whole image in the same time. So we try to correct aberration in the whole field of view when we do the optimization of the correlation. So there will be no kind of solution where you have something clear here and nothing there. You will try to really get things as clear as possible everywhere. That's what we do. But not only we do that, we could also, with correlation, do it different region. Because, for example, if we just select a small part of the image and do the correlation on this part, then it will only correct this part. But we will not be stuck at the part where the guide star is. Because if you only have a guide star there, it's going to be only there and not everywhere. So we have effectively more, let's say, flexibility of choosing correcting the whole field of view rather than some specific area surrounding the guide star, which is generally the problem you encounter when you do a guide star based adaptive optics in label-free microscopy. So advantage classically because you can go for sure faster. Disadvantage is that you have less flexibility because you are stuck with this guide star there, and you can only work with it. And case by case, some case it will work very well, some other case it will just not work very well.
So it depends on what is the spatial size of the object. If the size of the object is bigger, then I think this method will work better, right?
Yeah, probably. Yeah, probably. If you want to have something big and you correct everything, that's probably more useful than guide star approach. Yeah. But then after you can also have multiple guide star. If you have multiple guide star in your sample, then you're fine.
Okay, but, excellent. So you have to come front and ask the question. Yeah. So there's one more.
Yeah.
How much time does the optimization algorithm takes?
An hour. It's a minute per point, more or less. So if you do, I mean, here that's an example when we took a lot of points, but you can, if I show you there, they were maybe 7 points. So you can take like 5 points, scan 5 points per Zernike mode, 5 minutes per Zernike mode. So you have, I don't know, if you scan 10 modes, so it gives you to 50 minutes, more or less. So an hour, let's run it around an hour. That's basically the time it takes for the optimization in that case. And you have to be in weak aberration, because if you start, you see here the image I have at the beginning, I can see something. But if in a minute of acquisition, I have nothing there, then I cannot start the optimization. So this will be too noisy. And that's really a big, that's a big problem when I show you the image with stronger aberrations. It's not the fact that we cannot correct them. It's just the fact that we cannot start the optimization because we start from the noise. We are in the noise and we never get out of it. And to get out of the noise, you need to just increase the exposure time a bit more. So if the aberrations are too strong, then you need to increase much more than 1 minute. And then, then at some point it gets too long, and you just change your approach, because it's going to take you hours before you get something clean at the output.
Thank you.
Thanks. Any other question? Okay, I think we are done with our questions. So thank you so much. This is an excellent work. So thank you so much, Hugo. Let's thank Hugo one more time, I guess.